That's why we need to talk about the second type of queuing mechanism or algorithm, which is called fair queuing. Right. So the idea of FQ is to maintain a separate queue for each flow. Right? Currently being handled by the router. Right? So the router oversees these, or the router observes or serves these queues in a round-robin fashion. So let's try to understand this with the help of an example. So let's assume that we have one queue here for one flow. Say, let's assume that this is flow number 1. And we have a queue for flow number 1. Then there is another queue for the second flow. So let's say this is flow number 2. And then we have a queue for the third flow, or flow number 3. And then we have a queue for the fourth flow, say flow number 4. And what a router does is that it serves these queues in a sort of round-robin fashion. So what it does is it provides services to these queues in a round-robin fashion. It's a round-robin service, okay? Where the queue will first get a packet from flow 4, then it will get a packet from flow 3, then it will get a packet from flow 2, and then flow 1. So first of all, it will try to prevent flow to affect the transmission of the other flow. Now let's assume that let's assume the previous example that was creating a problem in first in, first out queuing. So we have an internet application, or say internet telephony. And say the data of internet telephony is being placed in flow 1. And then we have an application making use of TCP, and the queue number 2 has been attached to this flow. So what if the internet telephony keeps sending on the data at a faster rate? So these are all the packets that are queued here. So this queue will become full, and the router will start dropping packets from this queue that is being reserved for internet telephony. But on the other side, this is not affecting the transmission of the application that is making use of TCP, because there is a separate flow here, and we are placing the packets of this TCP flow in this queue, right? So clearly, this will overflow the buffer of internet telephony, and the packets will the router will start dropping packet from this queue, by not affecting the transmission or the flows of flows placed in the other queue, right? So when a queue reaches a particular length, additional packets belong to that queue. That flows queue are discarded, which is the case in this internet telephony, right? So by the way, this works well with with an end-to-end congestion control mechanism. Why? Because it is implicitly telling that or controlling the congestion control in the network, right? Or sending feedback, implicit feedback to the end machines. So the advantage of fair queuing is that it works well with an end-to-end congestion control mechanism. Right, but there are some complications. There are certain things that we need to consider here. So there are certain complications here that we need to identify, and then we need to look at its solution. So the complications about the fair queuing is that packets are being the packets being processed at a router are not necessarily of the same length. So the first complication is packets being processed are not necessarily of the same length. What do you mean by this? So let's assume that a TCP application, that this flow that contains a packet from a TCP application has a size of 1,000 bytes, right? And the size of this internet telephony application, the packet size of this internet telephoning application is 500 bytes. So if in a round robin fashion, if a router takes one packet from this queue and one packet from this queue, what do you think? Is it a fair allocation of the bandwidth? No, it is not. Why? Because the packet size of these two queues, the packet size of these two queues is not the same, right? So if we want to, truly allocate bandwidth in a fair manner, it is important to take packet length into consideration, right? So it is important, or it is necessary to take packet length into consideration. Okay. So what do you think? What is the solution of this complication or this problem? So we have identified a problem with the fair queuing, and now let's talk about its solution. The solution of this problem of variable packet lengths in different queues is to come up something similar to bit by bit round robin. But the problem is we just cannot do it. For example, we just cannot interleave the bits from different packets. This means what? We just cannot do that. We take one bit from here, from this packet, and then again take one bit from this packet, and then we keep doing this. This is not possible, right? So the problem implementing a bit by round robin is that it's not feasible. It's not feasible to interleave the bits from different packets. So this means that the fair queuing algorithm has to simulate the behavior of bit by bit round robin. Okay, so it has to simulate the behavior of bit by bit round robin. How? By determining when a packet would finish being transmitting. So a router has to identify when it will finish transmitting a packet if it were being sent using bit by bit round robin, and then it can use this finishing time to sequence the packets for transmission. So the solution is, how we would simulate this is, we will calculate, a router calculates the finishing time of a packet. Finishing time of packets. And then this finishing time is used to sequence. The packets for transmission. Right. So this means we have to calculate the finishing time of a packet for a specific flow. And if the finishing time is expressed in terms of how many clock ticks it takes to transmit a packet, then we can calculate this time. So what I'm saying is, if the length of the packet is expressed in terms of how many clock ticks it takes to be transmitted. So we can calculate the finishing time. How? We can calculate the finishing time with this formula, where f of I is equal to Si plus Pi. Okay, where this Pi denote the length of packet I. Okay, and Si denote the time when the router starts to transmit packet I, and this Fi denotes the time when router finishes transmitting packet I. So we can calculate this Fi, which is the time when a router will start finishing packet I, and it depends upon it's basically sum of Si, which is the time when a router starts to transmit packet I, plus the Pi, which is the length of the packet I, right? But there is a question that we need to answer. The question is, what do you think? When do we start transmitting packet I? What do you think, students? When do we actually start transmitting a packet I? So the answer to this question depends that whether packet I arrived before or after router finished transmitting packet I minus 1, the earlier packet, right? So when do we have to start transmitting packet I? It first of all depends upon that a packet I arrived before or after the transmission of packet I minus 1 from this flow. If it was after, then the first bit of the packet I is transmitted immediately after the last bit of packet I minus 1. It's also possible, by the way. So this means the starting time depends upon its arrival time. Either it's arrived before the completion of the previous packet or after the completion of the previous packet. So this there's another possibility. It's also possible that the router finished transmitting the previous packet, which was packet I minus 1, long before I arrived. So there was a gap between the arrival of packet I and the completion of packet I minus 1, right? So if we let AI denote the time packet I arrives at the router, then we can modify this SI, which is what? Which denotes the time when the router starts transmitting packet I, right? So we can modify. So we can say SI now is either maximum of FI minus 1. So this was the time when the router has finished transmitting the previous packet, which is I minus 1, or A I, which denotes the time when the packet I arrives at the router. So thus we can modify our original equation that is used to calculate Fi, which is the finishing time of packet I. Now the finishing time of packet I is maximum of Fi minus 1, the finishing time of packet I minus 1, the previous packet, or the arrival time of packet I plus the length of packet I. right? So for every flow, we calculate this Fi, and it means for every flow, we calculate Fi for each packet using the above formula, right? We're using this formula, right? And Fi is treated as timestamp. So this is very important. So this Fi is treated as timestamp. Right. And by the way, this timestamp is used to sequence the transmission of the packet, right? So this means a packet with lowest timestamp will be transmitted first, right? So we use Fi to calculate a timestamp, and then we use this timestamp to sequence the transmission of the packet. So this timestamp is used to sequence transmission packets. Of packets. So let's try to understand that how we use this timestamp to sequence the transmission of packets. So let's assume that we have a queue to monitor flow from one application. So this is queue number 1, and it is for, say, flow number 1, and it has 2 packets where one has the finishing time 5, and the other has, so the F is 8. Okay, and then we have another flow. This is flow number 2, and its F value is 10, right? And then this is the output link representing the transmission of this packet. So let's assume that this represents the packets from flow 1, and this color here represents the packet from flow 2. So what do you think, which flow will be first transmitted? What do you think, which packet will be first transmitted? Yes, you're right. So we will transmit first packets from the flow number 1. Why? Because their finishing time is less as compared to the packet from flow 2, right? So we will first, on this output link, we'll first put the packets from, we'll first sequence the packets from flow 1. Why? Because of their timestamp value, right? So we will then place, after placing the 2 packets from this flow 1, we'll get a packet from the flow 2. Why? Because it is based on the actual the completion time of the packets in flow 2. But there is also a problem with the fair tuning, that it does not consider this timestamp option while it is transmitting a packet from a queue, from a flow. So let's try to understand this. So let's assume that here we have flow 1, and in flow 1, a packet that has a finishing time, say 2, is arriving. So a packet is arriving. Okay, and then we have another flow number 2, queue for flow number 2, where a packet is in placed, and this represents the packet of, and obviously the timestamp or the finishing time of this packet is greater than the packet arriving in flow 1. Now, what will happen? What do you think? What will happen on this output link? which packet. So this, please note that it is transmitting. So what will happen? Yes, in this case, the router will first put F10 and then, the packet from the flow 2, and then it will place sequence packet from flow 1. Why? Because it was transmitting when a packet in flow 1 has started arriving. So the fair queuing does not take into consideration the scenario where of this timestamp where in a scenario where a packet is already being transmitting on the output link. Okay, so what are the advantages of, what do you think, what is the advantage of fair queuing? Yes. Number one, it's important to note that FQ, fair queuing, is work conserving. What do you mean by work conserving? This means that using fair queuing, a router will always transmit something on the network as far as there is a packet in a queue to be transmitted. And the second advantage is it provides a guaranteed minimum share of the bandwidth to each flow. It provides guaranteed minimum share of the bandwidth to each flow, as we have seen in this and previous examples. By the way, there are also different variations of fair queuing, such as weighted fair queuing, where we assign a weight. Where we assign a weight with each of these flow to select the specific number of packets from each flow, and then provide services to the other flow.